No, you're grounded.
You keep tech over there.
All right, here we go. We're here now. All right. So many things.
You have any idea how we did on the test?
Sorry about that. I had some trouble getting the live stream going.
Right, you do your homework. Homework in there. Hey, what'd you read
Hi.
Hello.
All right, wait, stop. Whatever y'all got going on, stop it. Put it away. Put it away. Keep it away. Don't let me grab it if I have to grab it. It's gonna be a problem for you. All right. So first thing is of course the do now. We'll talk about that in a second. We have a project coming up. This due soon, and then an exam. Okay. Similar to the last unit, the project is an easier or more straightforward thing to earn a higher grade on than a sit-down exam typically is. Though that's not necessarily always the case. Some students still score better on the test. On your matter test, I've not graded a section yet. I haven't even done it at all. During planning today, I will plan on scanning it, the multiple choice part. It's a pretty cool process. Have you ever seen that happen?
I think you get the right answers.
No, I just scan your, like I have an app that scans what you bubble in and compares it to the key grading, the multiple choice part. I sort of graded the short answer part, but that doesn't take as long as some tests. Anyway, so that's coming soon. Just be on the lookout for that. I'll probably be able to share the multiple choice points you earned, which will be, that's 75 points, 75 or 60 points worth of your test. That's towards the total of 108. You're trying to get to 108 points. So 75 puts you at 75 closer, depending on how many you get of that. Are you there? So that's what's going on there. Your project, I'll hand that out when it's more time for you to look at that more closely when we start talking about that today. But first, let's look about atoms. Before we even talk about the do now, let's think of it in these terms. This entire unit is called atomic theory. Everyone say atomic theory.
Atomic theory.
Atomic theory. The theory of atoms.
Atomic theory.
It's the theory. The theory of atoms is what we know now about atoms. Okay? What is taught now about atoms because of what we are relatively certain of, or mostly certain of, theoretically at least. Hello? The atomic theory. Atomic theory. Now it's taken a lot of time. This is the interesting part of this, or this is one piece of it. It's taken a lot of time for the atomic theory to come to us the way it has. It's been handled by many different transit authorities. Okay, it's been handled by many different people who studied the atom and used various tools, and so they made different thoughts that were modified later, and some have stuck the test of time. And how it's developed into what we learn today is of note, at least for us to kind of have as a background. And that's what the project is all about. The Atomic Theory Timeline Project is for you to put together a timeline of the development of the atomic theory. How was the theory? How did it kind of begin? How has it changed? How have people, students, thought about it? What would students have learned about it in 1826? Are you there? What would students have learned about it in the 1904? Okay? How would things have been taught based on what was known? Are you there? All right, and so there were various experiments and people along the way. You're going to chronicle those different parts along the way in the Atomic Theory Timeline Project. That's the point of that. But like I said, more on that later. I don't want to get into too deep onto that. The atomic theory essentially boils down to this. Now that we understand enough about it, everyone say atomic theory.
Atomic theory.
Everyone say the theory.
The theory.
Of atoms.
Of atoms.
It boils down to how we can observe these tiny little things that we now theorize. No one actually has like shaken hands with one, so it's still theoretical in that regard. Yet every test we run prevails to say they must be made, they must exist the way we think they do. Hello? We've tested, and the test, when we run these tests, we're like, okay, if it's not this test will fail. It passes. So it is that. Although normally tests are of negative nature. They're like, okay, if an atom and its particles are like this, then it'll pass this test. It fails it, so they're not like this. Are you there? So they say it's not this characteristic, not this one, not this one, not this one. Therefore, it must all be these characteristics, and that's what we learn in this class, in this unit. Hello? Ultimately, our goal is to represent atoms. Everyone say representing atoms.
Representing atoms.
Have you ever seen one?
No.
No, you can't. They're too little. They're little itty bitty guys and girls. So they're literally genderless. They don't really have that. There's no bathrooms for them. They don't have that equipment. So anyway, they're little itty bitty things, and we can't see them. So we have to represent. I want to say represent.
Represent.
Evan, that's not representing well right now. Because I don't know you have eyes up here. You don't. Representing atoms. Hello? Are you still following me right now? Okay. Let's see. I don't want to get too ahead of myself. But from the wait a minute. I know I have a slide on this one. Oh yeah. How did you go about drawing an atom from the do now? Because it said what?
I just copied
Oops,
one that's on the
no. Too fast. Draw the atom. Did you copy this?
Mhm.
Yeah.
Maybe where you drop little orbs in the middle?
Put the number.
You could have used numbers. What do you call that when you use the numbers? The Bohr model, right? Okay, so Bohr model is where I was trying to hint you towards, even though I gave you a non... This is still actually a Bohr model. It's just a fully pictorial Bohr model. How is Bohr model a little bit different than this?
As the numbers of protons and neutrons.
It has the numbers in the middle. What does this middle represent? The nucleus. So you're on your path to labeling it as well. Think about a way you draw it based on what you remember, how you remember it ought to be. Raise your hand if you've never seen a Bohr model ever. Raise your hand if you've never drawn a Bohr model ever. Hopefully you have, because that would present some issues on the periodic trends activity, since it asks you to draw Bohr models on it. So, okay, good. Let's see, and let's go straight ahead with a Bohr model. So what's this Bohr model? Let's see, we have here the nucleus. What are these little circles on the outside? Let's label this one first. Yeah, what is this whole deal here? That is the nucleus. What is? Well, I can bring the periodic table back down. We don't need it now. Yes, it's back. All right, the nucleus right there. What's in the nucleus? How do you know which is which? Protons are plus, and then the neutrons are these ones without a charge. They're the ends, yes? Okay. All right, so based on this, it's the protons, the neutrons, these are the neutrons, those are the protons. What are the green ones? Electrons. What do you call these rings? Electron shells or electron energy levels. Yes? You have something like that in your labeling? Okay. But yes, as you've noted and as we talked about, what should have spurred your thinking is to think of a Bohr model. Bohr model is probably the most common way in physical science that you come with for representing atoms. Bohr model. All right, and I'm going to have to modify a little bit of how I want, the way I want it done, but you'll quickly pick up on it. What do you draw first?
Circle.
Circle? How big?
Not that big.
What is this circle going to be?
Protons and neutrons.
The nucleus holds protons and neutrons. We're going to say P equals or colon and N equals or colon. But let's be consistent. We've been doing things in lowercase, so let's do P plus N 0. Let's be consistent with how we've been doing it. As long as you say P and N, I actually don't care about pluses and zeros in that case. All right. Then what do we have? Number of protons. How many protons were in the picture here? How many are in the picture here?
4.
You can see that there are 4. You can see there are 4 protons. Why do you say 6 though?
That's how many electrons there are.
Aha. Aha. This is a good thinking here. That's how many electrons there are. So you're presuming the atom's neutral. Does the atom have to be neutral? What do you call it if it's not neutral? An ion. And could it have differences in electrons and protons? Yeah, that's what an ion is. It has a different number of protons from electrons. Hello? All right, but let's go try it out. Just looking at the picture here, with 1, 2, 3, 4, 5 neutrons and 4 protons. Let's just go with what the picture is. 4 and 5. Yes? Which means 1, 2, we just use dots. Maybe you use a minus sign. 3, 4, 5, 6. All right. Several reasons why Jaden's thinking is correct. But I'm sure you may have come to it as well. You may not have, but that's why we want to correct it right now. All right, first thing, what is the element with 4 protons? That's beryllium. So then we would label this beryllium. It's Bohr model. Yes? However, how many valence electrons does beryllium have? It has 2 valence electrons with a total of 4 electrons. You with me? Beryllium is supposed to have 2 valence and 4 total. So if the protons say 4, then it's beryllium. Does that make sense? That's the identity marker. What we know about beryllium is it has 2 valence electrons. Does our picture have 2? No, our picture has 4. Okay, well that's okay. Ours has 4 valence electrons. But that's okay. Our picture has 4. That can be, that's not a big deal. That's just called an ion. Okay, well let's see if that's even legit. Let's take beryllium. Let's draw its Bohr model. P4, I keep wanting to go capital. P4N. How many would it have? 5? Yeah, that's about right there. Okay, 1, 2. Let's see, it has 1, 2, 3, 4 electrons when it's neutral. Does everyone follow me? That's beryllium's Bohr model. Let me know if I've lost you. Don't let me. Okay, because it's about to pivot to something a little bit more discrete. So I just want to make sure you see it. This is beryllium's Bohr model, and it differs from the one we had pictured. Okay? And we started out saying, okay, wait a minute. All we can see with our eyes is there are 4 protons. Do you understand where we're getting this from the picture? You only see 4 protons. So that's all we can be certain of. Therefore, if 4 protons, this is beryllium. It has a different number of valence. It has a different number of total. It has 4, and it has a total of 6. So what's wrong with it? We have to figure out why this is wrong. Like, what's going on? Well, if it's an ion, that's okay. That accounts for the different numbers of electrons. But real quick, what kind of ion does beryllium form? What kind of ion does beryllium form? Jaden said it? Everybody? 2+. Where does Jaden look for to notice that it's 2+? What? The column, above the column, we wrote the oxidation number. What's the oxidation number above beryllium's column? 2+. So when it's an ion, it's called beryllium 2+. What does the 2+ mean? Be careful now. If it had 2 extra electrons, then it has 2 extra negative things, and it'd be negative by 2. Is this negative by 2? So it does the opposite of extra. It loses 2. Has 2 fewer electrons, and which electrons does it lose? The outer one. So, loses 2. We put brackets around it, and now it's 2+ because it lost 2 electrons. Hello? That is how the Bohr model for beryllium can look as an ion. Beryllium's ionic Bohr model beryllium's neutral Bohr model? Does the one pictured match either of those? No. The one pictured here doesn't match either beryllium Bohr model. Hello? So, this is not beryllium. Aha. Aha. Which means the proton number is not 4. It must be another number. Jaden said 6 originally. Why could 6 make sense? Because it matches the number of electrons. What did you say, Mon?
Because you could take, since you take off 2.
Perhaps. Yeah, I don't know. Anyway, it could have 6 protons. Hello? That could just be in the picture. This could be a 3-dimensional clump, and maybe in the middle and maybe in the back, there's another proton somewhere that's just not pictured. Are you there? It has to be this way because we just ruled out it can't be only 4 protons. Because 4 protons means it's beryllium, and it's not any of beryllium's possibilities. Beryllium is only represented in 2 possible ways. Hello? It's not either of those. So there must be some hidden protons. We say 6 because we can match the electrons. But let's just walk through it real quick with 5. If it had 5 protons, then it would be what? Boron. And how many outer electrons could it have? 3. And what charge does boron, or what ion does boron form? B3 plus. So it's not Be, it's not Be. 2 plus. Boron and boron 3 plus. Boron 3 plus means it loses all 3 electrons in its outermost shell. So boron 3 plus, boron would look like this. 1, 2, 3, 4, 5. Boron 3 plus would look like this. 1, 2. Hello? Does that match our option again? That's why I just skipped 5. So it's not boron 3 plus. But it could be carbon. Carbon or carbon. What does carbon form? Na. It doesn't form anything. So it's really just, it could be carbon. Are you there right now? Okay. Good deal. Does carbon have 6 protons? Yes. Carbon can have 6 electrons when it's neutral? Yes. It has, how many valence electrons does carbon have? 4, because that's its group number. Hello? Stick with me here, y'all. Stay with me. It has 4 in its outer shell, so this could be carbon, and in fact, it is carbon. But let's do one more double check. How many neutrons does carbon usually have? How do you know that? Usual and picture. Protons, neutrons, electrons. Usually it's 6 when neutral, and then how many neutrons? There are 6 neutrons also. Are you there? Usually. Where do you get that 6 from? Okay, so not just any atomic mass. What did you do with the atomic mass first? Round it. And what does the rounded atomic mass indicate? The mass number of most abundant isotope. The rounded atomic mass is the mass number of the most abundant isotope. Please tell me that rings a bell.
Yes.
Oh, it doesn't? Okay, everybody, let's say it again. Trail me just a little bit. The rounded atomic mass is the mass number of the most abundant isotope. Hello? Most abundant isotope. The most abundant isotope of carbon has a total of these 2, which equals 12. Yes? 12 minus 6 gives you 6 neutrons. Most abundant is 12. Our picture shows that it has 5 in the picture. Hello? Is that realistic? What does 6 and 5 equal? 11. If it has 5 neutrons, what could you describe this carbon as being? An isotope? Is it the most abundant isotope? No. It's a non-most abundant isotope. Hello? Are you with me? But you could also say this. You could have 5 or 6. Are there 6 protons in this? No, there had to be 2 hidden. Is there enough room, perhaps, for maybe one more to be hidden? One more thing to be hidden? So couldn't one more neutron be hidden also? So you can count 5 neutrons, but couldn't a 6th one also be there? So you could have said this was neutrons 5 or 6. Are you okay? Now, this may seem like, all right, this is a review of physical science. In fact, let's double check you. I want you to hold up a 0, 1, or 2. 2 meaning, yeah, we're good. I'm good on this. 1 is like, okay, sort of remembering a little bit, but I'm gonna need some practice on these numbers and stuff like that. This is still a little shaky. I don't have a firm foundation. 1 and 0 is like, I'm just hanging on by a thread, or I don't know what's going on. Hold up at 0, 1, or 2. Okay, I'm just holding out hope for no zeros. 1s are great. 1s are fine. 2s are great. Because either way, I'm going to go forward as if you're all of 1. Michaela, go.
Can you go over the amount of electrons that can be in each cell? Because I think it's like 2, 8, and then.
Oh yeah. Oh, I've got a whole little diatribe on that. It's gonna be a lot of fun. Okay, and while we're on the issue here, we would say that this right here, this picture, if it's carbon with 5 neutrons, we would call it carbon 11. If it has 6 neutrons, then we would call it carbon 12. Hello? Several different ways we're representing this atom, just to skin this cat here. Okay? We want to see it this way. We have several different ways going on here. We have C11 versus C12. Another way to do it is called carbon 11 and carbon 12. Do you understand why I'm doing that? Why that all makes sense? What does this number represent? This and this are both considered the mass numbers. Yes? What is the mass number made up of? Protons plus neutrons. Right over here we have 6 plus 5. And over here we have 6 plus 6. Hello? That's where we get the 12 from. This is called isotopic notation. And we'll say isotopic notation. Specifically, this notation is called hyphen notation. Do you know why? Because there's a hyphen in listing the data. I'm going to ask you to do this on the test. I'm going to give you some details about an atom. I'm going to say an atom has 6 protons and 5 neutrons. Please write its hyphen notation. And then you'll have to do it. Or please pick out from the multiple choice options which one is its hyphen notation. Hello? Just look, that's the abbreviated, that's the longer version. There's another isotopic notation called symbol notation. Everyone say symbols. Symbols. So you take its symbol, and you put the mass number up top, and the proton number on the bottom. Hello? Hyphen notation and symbol notation. And then I might even tell you the symbol and ask you for some factors about it. All right, how many protons does this have? 6. How many electrons? You have to ask me a question first. Is it neutral? If neutral, then electrons equals 6. Hello? If not neutral, you have to consider its ionic status. We'll do an example of this in a moment. Hello? All right. So let's look at, all right, and then how many neutrons? And look at what symbol notation lets you do. Set it up like a subtraction sign. Take the top number minus the bottom number. 11 minus 6 equals 5, so 5 neutrons. Hello? Do you see this? 12 minus 6 is 5 neutrons, 6 protons, and if it's neutral, then 6 electrons. I don't know what I'm doing with that. That's 6. I got backwards on which one I was working on. Thank you. Good catch. Okay, are you there? All right, let's try this one then. Have you had to do something like this in physical science? Sort of, but not necessarily in symbol notation. Okay. So let's take calcium first. Actually, here's the ones we're going to do: calcium, aluminum, and chlorine. Wait, did you say chlorine? Oh, only bromine. Something right below it. Calcium, aluminum, and bromine. Are you following me right now? Let's do some different notations of these. And let's find out some factors about it. All right, so aluminum, or excuse me, calcium. Let's do it symbol notation. What would I start with? Ca. Okay. What next?
40 up top.
40 up top. Where'd you get 40 from?
Atomic number.
That's the atomic number. No, it's the mass number. What? Rounded. So if I take calcium and I say it's 40, then that means I'm saying it's the most abundant. Hello? All right. Calcium 40. This could also be called calcium 40. What goes on the lower number? Huh? 20. All right. How many protons? How many neutrons? How many electrons? We have two different possibilities. If it's neutral, how many electrons? 20. What if it's not? You say 18. Where'd you get 18 from? She looked at the oxidation number. If it's not neutral, what do you call an atom that's not neutral? An ion. When it's an ion, you need to know what its oxidation number is. Everyone say oxidation number. What oxidation number does calcium get? Ca2 plus. What does 2 plus indicate? It's positive by the loss of 2 electrons. Hello? Positive by the loss of 2 electrons. Positive by the loss of 2 electrons. Hello? So if it normally has 18 or 20, then it becomes 2 plus by losing 2. That's its only possibilities. You follow? So on a question I might ask is say, all right, here's some details. An atom has 20 protons, 20 neutrons, and is not neutral. Write its symbol notation. What's its atomic number? What's the mass number? Is that the most abundant or not? How many electrons does it have? Are you there? We would factor in all these different things. Are you following this? All right, let's start with aluminum from a different case. No, let's not do bromine. That's too easy. Let's do phosphorus, nitrogen. All right, so aluminum. Let's say I'm going to give you some factors of aluminum. I'll give you the symbol notation for aluminum. It's 29 over 13 aluminum. By the way, that's how you read it. So if I were to say, Evan, what is this symbol notation?
How many neutrons?
You say 29 over 13 AL. Say that.
29 over 13 AL.
That's it. That's how you read this symbol notation. 29 over 13 AL. By the way, this symbol notation is a way to represent atoms. It's a way to represent atoms for a purpose. What purpose is that? Tell some factors about it. Are you there? All right. So 29 over 13 aluminum. What would you call this, Michaela?
29 over 13.
Perfect. That's exactly right. Okay, good. Just making sure you're on your toes there. All right. So AJ, what is the mass number for this symbol notation? This symbol notation represents a specific isotope. What's the mass number? 29. This top number is the mass number.
27?
No, 29.
Isn't it 27 up there?
What am I showing you right here?
29.
An isotope aluminum 29. What is aluminum 27? Aluminum 27 is the most abundant. Aluminum 27 is the most abundant. That means in nature, if I were to survey the number of aluminum atoms out there, I would find the most aluminum 27s. Does that mean I will never find an aluminum 29? No, I could find aluminum 29. It would just be rare, not abundant. Hello? So do you see what you already figured out? You didn't make the connection yet, but some of you are like, hold on, the mass number should be 27. But right here it shows it's 29. Why is it different? Exactly. It is different because 27 is the most abundant mass number isotope. Hello? 29 is not most abundant. You just determine that detail if they don't match up. Hello? All right. Cam, how many protons does it have? $13. What number tells you the number of protons? The atomic number, which is 13. You could either look at AL and then find it up there as 13, but realize that this bottom number is always the atomic number. Hello? Okay. Let's see. Protons are 13. Zach, how many neutrons?
13. No, 16.
16. How'd you get 16?
Subtract top and bottom.
29 minus 13 is 16. Are you there? I think that's how you get the number of neutrons. How many electrons does it have, Bryce?
Yeah. I couldn't tell you.
Well, what is the true of the electron number compared to the proton number?
It's supposed to be the same.
They're usually the same when?
When it's neutral.
Okay, so tell me what it could be then.
13.
13 if what?
Neutral.
That's a way to say it. You could be like, well, I don't know if it's neutral or not, Mr. Knight. That's okay. If you said 13 if neutral, you're right. But you could also be right if you gave me a different number. Ian, what's the other number?
10.
10. Where'd you get 10 from?
It's 3 minus the 13.
Close.
plus.
is 3 plus. So aluminum has ideas of becoming an ion. It's called aluminum 3 plus. 3 plus means loses 3 electrons. So how many electrons does this one have? 10. If it's not neutral. You see it? Do you see how you can get that answer every time? Either by saying this if neutral, this if not. And you might stick with here a lot of times, but what if I say specifically, if I ask this question one of two ways? I would say, all right, aluminum 29. What's the mass number? 29. I'm going to look there. Is that the most abundant? No. How many protons? 13. How many neutrons? 29 minus 13 is 16. How many electrons if it's not neutral? There's only one answer. If I just say how many electrons, you can pick either one. You just have to justify. Well, 13 if neutral. Or you can say, well, 10 if it's not neutral. Or just say 10 if it's not. I'll know what you mean. Are you there? And then if I could ask the question though, how many electrons if it's neutral? Or I could say, how many electrons if it's not neutral? The answer 10. Are you following this? Do you see how to do this various different ways? These are the skills. You're practicing them in pieces right here. And we've represented atoms in some ways here already. So I want to go to a certain slide real quick. I want to skip some things to really hammer this down a little bit. Let's see. Is it A on top or Z on top? Hold on. All right, well, I'm just going to go back over here then. Different parts. Okay. Here's the way we generalize symbol notation. General symbol notation is you put the element symbol in the superscript off to the left. You put what's called the A number. The A number is also called the mass number, which is funny because it's not just any number, it's A number. No, not A number, it's the A number. A number is the mass number. And get it? Because the mass number is a number. But it's not only a number, it's the A number. Mass number is a number. No, it's the A number. Number. A. Mass number is a number. The A number. It's called the A number. It's the A number. So it goes in the place of the A spot. It's the A number. I don't know if you're getting it yet. But A number. And the best part is the proton number, the atomic number down the bottom, goes on the bottom. It's called Z number. So you're like, what number do you put on the bottom? Z number. Not just Z number, but the Z number. The Z number. Z number goes on the bottom. And a number goes up top. Just a number up top and Z number on the bottom. Okay? Am I right? Okay. Alright, okay. We'll talk to Boris and we'll talk later, okay? Wow. Are you there? Okay. I'm just checking on you. You seem like you're not, okay? He's crazy, man. Man, if we were on YouTube Live, I'd tell a story right now I heard recently.
You want to know a story I heard yesterday? I
Nobody
heard that you don't like your first
I
period.
mean, nobody's watching.
Who
Somebody
on
told me
earth is
that.
saying that?
My friend, we were in third period together. She said, "You're in his first period, right?" I said, "Yeah." She goes, "I heard he don't like his first period."
Who on earth? First of
dare
all,
you say
first
that?
of all, I do not talk about liking or disliking a period to another class period. The extent that I share is usually about a period dragging or not, like you guys are tired or like behavior-wise or something explodes or something like that, like behavior-wise. That will get a mention, but that hasn't happened. Hasn't happened even this semester. Like I haven't even mentioned that something has happened in it earlier. Like you guys have been great. You guys have been great. You guys have been great. So yeah, that was a false thing.
That was a false
And if they try to explain the context to me, tell me the context, and I'll be like, hold on, did I say that? Let me explain the context again. It's probably a misinformed context. Anyway, no, I don't feel like that. I haven't shared like that. But I would tell you if I did. Tell them, yeah, I told them you guys were dragging. You guys, I feel like I was dragging you guys by a rope, and you guys were just like this. Behind me as I dragged you because you were so tired in the morning. And I was just tugging along, just yanking and just trying to so badly get you up here.
You ever thought about being a mom?
Is what I imagine. That's like if I'm dragging you by a rope. But that hasn't happened yet. Now, will I say, did a fall class period or two get dragged like that? I have to carry the whole class as if by, come on, Santa's bag over here? No. Yes, it happens in fall. The fall. There were several days where class periods were drug along. Eek. Okay. Anyway, you here with me right now? Okay. The number. We have our notations here. We have isotopic. We have hyphen notation. We have symbol notation. Oh, look, even better, abbreviated symbol notation. We can abbreviate. This is such a time saver. Y'all, this is crazy. See carbon in its symbol notation? Its complete symbol notation. Look at the shorter version. Wow. Thank you for saving us time. I'm being sarcastic. Don't really say that next time. Try one digit. And complete symbol notation lets you see the subtraction a little bit better. The abbreviation, you just drop off the atomic number. Because saying the atomic number and the symbol is redundant. The symbol means 6. The atomic number means 6. That's just what it is. It's an identity marker. It's to be redundant. Are you guys okay?
Yeah.
I still want you okay? Let's see what else we got
We need
here.
new accents.
You don't like my Russian accent?
I want to hear more.
You don't need to go to others. Okay.
Yeah, that's the one you got. Wait, that was
A couple other things just to point out. We got the nucleus, we got the energy levels. We got the picture, we got versus actual, neutral versus not, right? Isotopic means different numbers of neutrons, and ion means a different number of electrons. And then you have identity, right? ID is a different proton number, right? It changes its identity. You can change the proton number. So you have 3 I's going on here. Three-eyed monster. Okay, what else is there to say of the things? Oh, let's do nitrogen. Let's do nitrogen real quick. This will be a good one. Good one to end on. Nitrogen. Let's say it's nitrogen 13 over 7. That's its symbol. All right, let's scatter around. Daisy. What's its mass number?
13.
Where'd you get that? The A number. The A number. That's too many articles. The A number. It's A number, okay? Move on. 13. You're right. Is that the most abundant isotope of nitrogen? No. What is the most abundant isotope? 14 over 7, excuse me, 14 over 7 nitrogen, or nitrogen 14 is the way you could name it also. Hello? Not abundant. That's one way I can do it to save time. How many protons, Macy?
7.
It is 7. Yep, because that bottom number is the proton number. It's also the atomic number. Good job. Bryson, how many neutrons?
That's electrons.
I'll let you do the electron. 7 if neutral.
Okay.
I'm going to say 7 if, just to save time. I'm going to think of ways to save time. 7 if, since you went with the easy route, what if it's not neutral?
6. 'Cause it loses one.
Oh no, it would be.
Let Brassen do it.
So it's
If
minus-
it's not neutral, what does it form? What do you call the thing that it forms if it's not neutral? An ion. What ion does nitrogen form?
Shut up.
1 minus.
Is it 1 minus? Check your periodic table. Don't answer, just let him do it. You got that one too, yeah, but you also have that on. You also have the charges and
3
stuff.
minus.
Huh? 3
3 minus.
minus. So how many electrons does it have if it's not neutral? In 3 minus. What does it mean to be 3 minus?
Gain 3.
Has 3 extra electrons. Say 3 extra electrons.
3 extra electrons.
Just say that to yourself, okay? Now answer this question. How many electrons does it have total if it's not neutral? 10. Because 3 extra on 7 is 10. Hello? This is good. This was good. Very good. Now we can get a neutron answer. Caitlin. 6. Where'd you get that? Be careful. This is the mass number. So you subtracted mass number minus 7. Minus the atomic number. Now, how many neutrons would this one have had? 7. Do you see why this one has 7? You okay? We're going to practice these some more in a little while, but maybe tomorrow. I just want to make sure you're not totally gone. Okay, and then to answer your question, Michaela, you asked earlier. Let's see, I may have to erase some of this mess. Oops. Oh yeah, this is good. Okay, general notation, Bohr model, good. 2 isotopes, carbon 11, carbon 12, the energy levels. So if I said right here, if I had the difference here on oxygen 18 and oxygen 16, what is the difference between them? The mass numbers are different, 18 versus 16. Now here's the follow-up question. Why is the mass number different? Because the neutrons numbers are different. Are you there? How many neutrons does this one have? 10. How many does this one have? 8. Hello? Can you see that? Okay, this is all being live streamed too, so you can go back and hear my Russian accent, of course. If you must, but I don't encourage that per se. So again, here we have oxygen 18 versus oxygen 16. Good. That's actually a different question altogether. Oh good, yes. Totally yes. Ooh. All right. So Michaela, you're gonna help us out right here. This is crazy, y'all. This is crazy awesome. Woo!
Whoa, you dropped it. That's a lot of shells.
That wasn't it. We haven't done it yet. So the question you've probably Michaela asked. You said how many electrons fit in each orbital again. I can't remember exactly. So we're gonna go with we're gonna learn some about this. And we're going to use our periodic table to help us. Okay. So first, remember this, the periodic table, yours looks like this, but in actuality, it's supposed to look like this. Hey Jerry, you still with us? This is how it's supposed to be all stretched out. You know what might be helpful? Is if you had this in front of you to look at. That has to do with another type of representation.
I know you can now. I know you want to. They have everything. You have to do it. They have to have one in Dublin.
I have to?
Yeah.
This is huge.
Am I doing
Look, for the first one, this is not exactly.
You would never have to. You would. You would never have to wait.
I haven't done it in a while because, you know,
Oh, dude, I
people
love
are
that
too soft.
I don't really care. So.
I know. The biggest thing is not to be recorded. But yeah, when that goes off. All right, so check this out. Now you have this example in front of you. This is how the periodic table is actually laid out. The SPDF, I'm about to illuminate a little bit, but you're going to understand that's actually used in later interpretations of representing atoms called electron configurations. Now we're getting into this a little earlier than I wanted to, but Michaela asked it, and I want to get into it too, just to give you a little primer, because I think you're going to like it. All right, so check this out. Scientists have done this. They've labeled the sections. They looked at the periodic table and said, this is the best way it's laid out, because this is all how the characteristics line up. This is how commonalities line up. Remember, it's arranged by increasing atomic number into groups into periods, by cycling common characteristics, which gives rise to trends. Remember that little saying I had you say over and over again? Are you still following me right now? Okay. So when they laid it out like this, it looks like this shape. Makes this weird looking shape. And really even more so, over here, you get the other 1s. Helium, for the shape of the periodic table, helium belongs over here. Okay, so pretend it's not here. You just got this shape, this shape, this shape, and this shape. Everybody there? Do you understand that? Now, there's a reason why they've chosen these letters, but here's what they've essentially done. Is they've taken the shapes and they said, here's what we're going to label these shapes. We're going to say the 2-column shape, right here, 2-column shape, skinny, tall, rectangle, they called the S shape. You'll see why later. They called the shape right here, without helium, they called the P shape. They called the transition metal block the D shape. And they called the other one in between, that usually sits below, they called the F block. Are you there? And notice here, lutetium and lawrencium, these two right here, they fall in right in this spot, below scandium and yttrium. Scandium, yttrium, lutetium, lawrencium. Are you there? Whereas lanthanum and actinum are the beginning of the 4F and the 5F rows. Are you following me right now? All right. Wow. Yeah, this is great. Okay. Everybody understand that's just what they did. This just is what it is. The periodic table is made of shapes. They named each shape SPDF. That's the order they say them. Are you there? All right. Woo-wee. Y'all, about to get you right now. So I've even rearranged it with the helium over here. All right. What does the period or row number tell us? number of energy levels used by those elements, right? So hydrogen and helium only ever use the first energy level. Okay. How many without looking at what it is, how many squares, tiles are on row 1? 1, 2. Are you there? There's only in all of row 1. You see this? In all of row 1, there's only 2 tiles. And the period 1 or row 1 means energy levels. Yes? So, how many energy levels can how many electrons can the first energy level have? 2 electrons. Row 1 has 2 columns on it. See, row 1 has 2 columns on it. Therefore, it holds 2 electrons. The period means energy level. The number of tiles on that row is 2. 2 columns on that row. 2 columns. Hello?
Oh.
That's the max in the first row. Yeah, it just got real. It is crazy. All right. Second energy level. How many tiles are on the second energy level? 1, 2, 3, 4, 5, 6, 7, 8.
Ain't no way.
8.
I did not know that.
How many electrons can the second energy level hold?
1.
Oh.
So not,
Because it's 2 plus 6.
how long were you going to keep this to yourself?
Not very long. Not much longer. Maybe another day or 2. All right. Third energy level. Let's watch this. Look at row 3. How many columns are on row 3? 2 plus 6 again. 2 plus 6. You might say 8. But hold on. Do you remember how many are in that row? Do you remember how many electrons are in the third energy level? If you remember from a past class, you may have heard 18 though. You're like, hold on. If I count the row, hold on. Row 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 on row 3, on period 3. So it should be a max of 8. But my teachers before have told me it's 18. And that's from the textbook, and they don't lie a lot. I mean, that's consistently true. The third energy level holds 18. Well, where did the other 10 come from? Emily's looking at her long periodic table sheet that I handed out a second ago. Where do you get 10 more tiles? The transition metals, but wait, transition metals start on row 4 technically, but wait, why would you look at transition metals on your page here?
You gotta add in that bottom.
What does it say on the first transition row? What does it say? What was the number in front?
3.
Huh?
3.
3. Hold on. So that means this third row, or this row of the D block, actually behaves, its electrons behave one size smaller.
Holy cow.
So yeah, it's on row 4, but it behaves as if it's row 3.
That's crazy.
And this behaves as if it's row 4, and then 5, and then row 6. Does that jive with your page? Does that match up 3D, 4D, 5D, 6D?
I'm not getting confused.
Do you see that on your page? So when we count electrons on the third energy level, you look at the row, 1, 2, 3, 4, 5, 6, 7, 8. But you also look at the D block lifts up, it elevates up. Those electrons act smaller. And this is, look, here's the reason. The electrons want to take the lowest energy possible that they can survive in. Are you there? So they want to drop down, and it just by natural circumstance, it shrinks inside the fourth energy level. It does not act like a fourth energy level. You might still say, look, this is on row 4. Mr. Knight, what you're telling us about the rows and how many things are on that row tell you max electrons. Hold on, that's on row 4. It should be like row 4. Well, they don't behave like you want them to. It's not that simple. It's a little more difficult. These row 4 atoms and their electrons behave like a third energy level. They're smaller than fourth energy level. Hello? Are you picking up right now? And just count with me real quick. How many tiles are in this first one right here? 1,
2, 3, 4, 5, 6, 7, 8, 9, 10. Oh,
10.
Found them.
Plus 8.
We found them.
And this is going to make more sense soon. So everything raises up 1 energy level. So that the 18 is 2 plus 6 plus 10. Hello? Now watch this. Let's look at this. Whew. Before we keep going, because at first you might say, okay, good. Look at row 4. Let's count row 4. Count it with me. Ready? 1, 2, 3, 4, 5, 6, 7, 8. Why did I skip this? Because that counts as row 3. Look at your long one and see why that it has a 3 in front of it. Yes? So let's count again. Ready? 1, 2, 3, 4, 5, 6, 7, 8 on the periodic table. Then count down the D again. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Just for those at home. This is row 4. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Hello? Y'all, this is about to add to it. 18. So you might think 18, right? Because 2 plus 6 plus 10 gives you 18, right? Pause on that. When we counted electrons, when we counted electrons on row 1, how many shapes did I pass through? No, I did 1, 2. On row 1, they were all in the S shape. Yes? So I only counted tiles in one shape. Yes? Row 1, one shape. How many shapes do I pass through when I counted them on row 2? Two shapes. Row 2, I counted tiles in 2 shapes. Are you still with me? Which is why when I added these up, when I added these up, I said 2 plus 6. Row 1, I added 2. Row 2, I added 2 plus 6. Row 3, how many shapes do I count through? 1, 2. I'm missing a line here, sorry y'all. That'd be why it's so counted wrong. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Then count 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Row 3, how many shapes did I count through? S, P, D. 3 shapes. Row 1, how many shapes? 1. Row 2, how many shapes? 2. Row 3, how many shapes? 3. Row 4, how many shapes would you predict? 4. Which means row 4, I'm going to go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14, 15, 16, 17, 18 is what I counted on. 18, that's 3 shapes. And then 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So how many electrons are over here? How many how about this? How many columns are in that F shape? How many columns are there in the F shape? 14. So plus 14. Columns, y'all, 14. Columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hello? So 2 plus 6 plus 10 plus 14 is 32 max. And then that number repeats again because our periodic table is limited. But you notice here the F, what's the first row in the F block say? 4F. So it gets counted with the 4s. Hello? Then again we go 32 here again, and then we're at 18 again. 6 goes down to this 5 goes to 4, and then 5, 6. Okay, so 18, and it should be 18 again. Are you there? But that's reality. That's how things have been because our periodic table stops after a point. If the pattern continues, how many electrons would theoretically fit in here? What's the pattern here? 2. 2 plus 6. 2 plus 6 plus 10. 2 plus 6 plus 10 plus 14. 2 plus 6 plus 10 plus 14 plus 18.
It's the number plus.
So 50. And maybe you don't see that pattern as well. What's 2 divided by 2? 1. What's 6 divided by 2? What's 10 divided by 2? What's 14 divided by 2? What comes next? 1, 3, 5, 7, 9. What comes next after 9? What comes next after 11? Hello? So 2 plus 6 is really 1 doubled plus 3 doubled. You with me? 2 plus 6 plus 10 is 1 doubled plus 3 doubled plus 5 doubled. 2 plus 6 plus 10 plus 14 is 1, 3, 5, 7 doubled and added together. 50 we get by saying 1, 3, 5, 7, 9 all doubled added together. What would be the theoretical on the next one? What's 11 doubled? 22. 22 plus 50. What's 13 doubled? 26. What's 26 and 72? So that's how many. These are all theoretical because our periodic table is limited. What if there were no limits, like heaven or something?
That's crazy.
You'd be like, heaven does not include chemistry for me, so. Wow. Are you there now? Is your mind blown right now? Wow. Whoa. Wow.
I reached this several times because it's like, yeah, it's this is a lot of work.
This is that what it's supposed to say?
Yes.
Where's the top 2 ones, right?
It was one of the 220 question ones. I said I'm looking for your highest score on.
Okay, so like, I don't have to do one of them if I already made 100 on the other.
If you made 100, your highest score, you don't have to do it. At this point, no. If this were before test day, I would say we'll take them all anyway just to help you get better at it.
Yeah.
So, but at this point, no. Just to get the grade.
First try.
You can mind.
It's on the matter one though. That one was pretty easy. I don't know about the other one.
Both of the data, I'm at 95 and 100.
That's not still bad though.
about this project. I'm finishing it. Finish it. I'm not gonna
I also do the quizzes. I'll tell you what period I started doing them, and then I started asking questions about the elements, and I didn't have my periodic table with me. The countdown was going, and I was like, I'm running down my periodic table.
I can tell this one goes better than this one. I've never done this. Same with this one. I do like
There's a lot of words. My brain is I'll make it better.
Oh, it's
We have that too. But that's what Jesse taught me. It wasn't
Great
anything,
energy.
but then Jesse came in, we had a rope and everything. We just wrapped it around it.
Yeah. Thanks for nothing. Why are you tapping me? You and your tapping stuff. Sit on your hands. Tapping. Oh, little kid, sit on your hands.
I don't like.
What?
I mean, I just don't buy it. It comes in with buys and I have extra time in the morning that road. You do that and buys together. So like, how many buys?
All right, so the timeline project here, check it out. Remember, the atomic theory has been developed over the course of time. Okay, so it began with how do we know they exist? Like what's going on? Some people with time on their hands. This guy named Empedocles, 470 BC, was like, what is everything made of? He's like, all things are made of earth, air, water, fire. And he didn't have a scientific method. He wasn't like, all right, if everything's made of fire and I test it this way, then this will prove it's made of fire. He didn't do that. He just thought, these are the four basic elements of all things that make us happy. Therefore, they must all be components of everything. And in various combos, we get the Kamehameha. No. None of that. No, he didn't say that. He was a philosopher who made a scientific imposition. Democritus came on later and was like, actually, that doesn't sound right. Like, because if I take a rock and I keep busting it up into small pieces, I bust it into such a small part that I can't see it. At some point, I won't be able to see it. And he said, and it probably is indivisible. He's supposed. He had a very crude science project. And he was like, I'm going to call that an atomos. In the Greek, just means you cannot cut it anymore. So it's a particle you can't cut anymore. He called it an atomos. He came up with the first word. And then he wasn't very well liked or well known because later in 250, Aristotle, another philosopher, was like, no, I don't know this Democritus fellow, but everything is earth, air, water, fire. And I'm Aristotle. And for almost 2,000 years, Aristotle, because he was famous, we believed him because he was famous. It should be a lesson in like history, like we don't just trust people because they're famous. We trust them because they're right, because they make sense, because it's logical. So he's like, no, Democritus, what are atomos? That's ridiculous. Earth, air, water, fire. That's the smallest things. Well, he was wrong. Democritus was right, but he was ignored because he wasn't as famous as Aristotle. Kim Kardashian, just a guy. Just someone else with their own TikTok channel. 23 followers. All family members.
I'm actually that same way.
The most people followed on TikTok. Making old-fashioned videos. Anyway, atomic theory is developed. It started with these folks and it moved forward to the atomic structure that we have today. So, that's kind of the end of it in terms of what I would cover from a historical standpoint. Now, I have slides online which you can access on the atomic theory folders on Google Drive. And I would go there to help you. But this project is mainly about you gathering information on the history. Which one? This one? Okay. So, like I said, there are more slides on the history, but we're going to fly through those in class. You should go peruse them on your own.
These are on Google Classroom?
These are on Google Classroom. You should go peruse those on your own or in Google Drive. They're in Google Drive.
Okay.
picture of the tasks, so I can erase this for this new unit. This would be like history. I think it's even labeled history or something or another. So, O2 atomic theory.
I don't wanna read all that. Where's
I'm
it said?
saying at this point, like, usually I don't look forward to school.
Look at all the way down. Seven, look at
No, I'm
C.
just looking forward to
This
get
is
out of
clearly where you
this
go.
class.
If I hear somebody say, go to C, I'm gonna go, this is C. No, you didn't. You'll see ready to go. 3 slides per person. So we're going.
So yeah, I'm letting you go look at your project a little bit, but yeah, here's how it goes. The project is you and perhaps a group will put together a timeline. You can use slides, you can use poster board, you can use some other online tools that allows you maybe make an interactive timeline. But a timeline shows events that happened over the period of time. Yes?
Yes.
You're going to do this as well with some conditions. This is your conditions. Okay, here are the conditions. First, you can do this all by yourself. You can do all eight events. I call an event or a point on the timeline, I'm calling them entries. So when I say entry, that's what that means. We're going to break this down more tomorrow, but for now, you look at it. Your homework is to look over that, look at the history, you can pack it up, and we'll see you tomorrow. Go Dogs.
Thanks for watching. Tune in next time for another edition of Night Chemistry.